In this video, we're going to look at what it means for a system to be in dynamic equilibrium. To begin, I'd like to define three terms that will help us in this conversation. The first is rate or rate of reaction, and this describes how quickly a reaction proceeds. This can be described as how quickly reactants become products. Now, there's a variety of ways that you can measure this, but it's typically going to be in something such as moles per minute, moles per second, maybe millimole per second, or if you're talking about a solution, maybe something like molarity per second. That is to say, some quantity over time or some concentration over time. The second term is reversibility. In general here, some reactions proceed in both directions. To best describe that, I'm going to give an example. Many reactions that we've studied proceed only in one direction. Consider the combustion of methane to form carbon dioxide and water. There, methane reacts with oxygen to form CO2 and H2O, but CO2 and H2O do not reform methane and oxygen. On the other hand, consider the Haber process, where nitrogen reacts with hydrogen. In that reaction, nitrogen and hydrogen will react to form ammonia, but ammonia will also decompose to reform nitrogen and hydrogen. That reaction is reversible, proceeds in both directions. Perhaps the best way to envision this is with a diagram. If you begin a reaction with a container that has just hydrogen and nitrogen in it, you might think that at the end of that reaction, you would get all ammonia. Well, that's actually not the case, because in reality, some ammonia is formed, yes, but some of that ammonia also decomposes to reform nitrogen and hydrogen, meaning that at the end of this reaction, there's a mixture of products and reactants in the reaction chamber. The final term I'd like to discuss in our conversation about equilibrium is, of course, equilibrium itself. And this is a situation where the forward and reverse rates of reaction are equal. And what I'd like to highlight here is we're talking about rates. So equilibrium is when the rates of reaction are equal, not necessarily when the concentrations of reactant and product are equal. Now, we've seen equilibrium before. We saw it in talking about the evaporation and condensation of a liquid, where a liquid might evaporate into the gas phase, and some of that gas might recondense into the liquid phase. That creates a dynamic equilibrium. And we also saw it in talking about solubility. And at the saturation point, a solid is dissolving at the same rate that dissolved particles are resolidifying. Those are both really good examples of equilibrium where the forward and reverse rates of those reactions are equal. We can show the reaction of the evaporation and condensation by talking about liquid water being in equilibrium with gaseous water. Note the reversibility of that reaction. And we can talk about the equilibrium of dissolving and precipitating by looking at solid sodium chloride being in equilibrium with aqueous sodium ions and aqueous chloride ions. And again, the key here is that the rates are equal, not necessarily the concentrations. To give another example of equilibrium, I'd like to use an analogy of students moving between classrooms. Consider two classrooms. We'll consider a classroom here called room 121 and a classroom here called room 123. In room 21, perhaps there are 10 students at the beginning of our experiment, and in room 123, perhaps there are 30 students. What I'd like to do is map the movement of those students across different times. So we'll have a time of 0, 1, 2, 3, 4, and 5. The unit on time is not so important here. At time equals 0, of course, there are 10 students in the one room and 30 students in the other room. But there's going to be some movement between these rooms. Room 123 is really crowded, so there might be a large movement of students out of room 123, maybe at a rate of 6 students per minute. Likewise, even though room 121 has a little bit more space in it, perhaps there's still some students that want to see what's going on in room 123. So there's a slow rate of students leaving room 121, perhaps at a rate of 2 students per minute. So let's look at what's going to happen after the first minute. After 1 minute, 6 students will leave room 123, but 2 more will come back. That's a net loss of 4 students, dropping the number to 26 students in that room. At the same time, after 1 minute in room 121, 6 students will have joined, but 2 will have left, for a net increase of 4 students, bring it up to 14 students. Let's modify those numbers. And now let's think about the rates. Now there are fewer students in room 123, so we might expect that the rate will decrease a little bit. Fewer students want to leave because it's less crowded. At the same time, there's more students in room 121. It's getting a little bit more crowded, so more students might want to leave. Now let's consider what happens after another minute. 5 students leave room 123, but 3 come back. That's a net decrease of 2 students. 5 students join room 121, yet 3 leave. That's a net increase of 2 students. Let's adjust our numbers one more time, 16 and 24, and think about the impact that will have on the rate. There's now new concentrations of students and therefore new rates. Fewer students in room 123 means fewer students are leaving. But more students in room 121 means more students are leaving that room. Let's look at what happens in the next minute. 4 students leave room 123 and 4 come back. Well, there's no net change there. There's new students, but there's no net change in the number of students. In room 121, 4 students arrive and 4 students leave. Likewise, there's no change in the number of students. With no change in the number of students, or the concentration of students, there's no longer a change in the rate of reaction, so this reaction can continue proceeding at the same rates, and therefore there'll be no more change in the concentration, meaning in minute 5, there will also be the same number of students. What you can see here are 2 important points that characterize equilibrium. The rates of reaction are equal, but the concentrations, or the numbers of students, not necessarily equal. That's a really important concept to keep in mind with equilibrium. Moving away from an analogy of students between classrooms, I'd like to look at a graph describing this exact idea, concentration and rate. Here I've got 2 separate graphs. The top graph graphing rate across time, the bottom graph graphing concentration across time. For the bottom graph, I'm going to use red to represent my reactants, and I'm going to use blue to represent my products. For the top graph, I'm going to use red to represent a forward rate of reaction, and blue to represent a reverse rate of reaction. It's not so important what this reaction is. It's some fictional reaction where we have A plus B yielding C and D, but it is important that it is a reversible reaction where C and D can also reform A and B. Let's envision a situation where we start with lots of reactant, lots of A and B, and very, very little C and D. Because the concentration of A and B is very high, the forward rate of reaction should also be very high. There's lots of reactant, lots of ability for collisions, lots of ability for that to become product. Likewise, with very, very little C and D, very little product, the reverse rate of reaction is very slow. Now, let's consider what happens over the first few moments here. Because the forward rate of reaction is very fast, A and B are becoming C and D faster than C and D are becoming A and B. What that's going to do is decrease the concentrations of A and B. As the concentration of A and B decrease, well, they're becoming C and D. That's going to increase the concentration of C and D. Let's consider those effects on the rate. If the concentration of A and B are going down, then the rate of A and B reacting, or the forward rate of reaction, should also be going down. And if the concentration of C and D are going up, the rate of C and D reacting, or the reverse rate of reaction, should also be going up. Now let's consider the next point in this graph. The concentration of A and B has decreased, but the forward rate is still faster than the reverse rate. That forward rate, while slower, is still faster than the reverse rate, which means in the next instance here, there will still be a net decrease in the amount of A and B. And for every amount of A and B that decreases, well, there's got to be an increase in C and D. Let's consider these new concentrations and the effects they have on rate. With much, much less A and B, the forward rate is going to decrease. And with much more C and D, the reverse rate is going to increase. Now, the cause and effect is important to think about here. Let's shift our attention to the rate, which is going to cause a potential change in the concentrations. The rates now appear to be equal. The forward rate equals the reverse rate of reaction. The rate of A and B forming C and D is equal to the rate of C and D forming A and B. At that case, there's still a reaction taking place, but there's no net movement from reactants to products. So there's no longer a change in the concentrations. Those concentrations hold steady. Because the concentrations aren't changing, the rate is not changing either. What we've now established is something called dynamic equilibrium. Dynamic because the reaction is still occurring, equilibrium because the rates are equal. Let's divide this graph into two separate pieces. We have a dynamic phase, a phase where the rates are changing or the concentrations are changing, and we have an equilibrium phase. The equilibrium phase where the rates are equal or while the concentrations are constant. What's important to note here is that the rates are equal, but the concentrations are not. We can learn a little bit more about this reaction. We can see that a very small concentration of A and B reacts at the same rate as a very large concentration of C and D. That tells us it takes a lot of C and D to generate the same rate of reaction as very, very little A and B. To wrap up our conversation, I'd like to tie these ideas together with a good graphic. Consider a reaction A and B. You have a flask that contains a solution of just A and just B. The reaction begins, however, there's no products yet formed. There's a high rate of collision between A and B, and again, that forward rate of reaction is very high. At some intermediary point of this reaction, the collisions between the reactants will begin to decrease as the concentrations of them decrease. The rate of the forward reaction decreases, and that reverse reaction begins. After a period of time, this reaction will settle out or come to equilibrium. The rate of the forward reaction equals the rate of the reverse reaction, dynamic equilibrium is established, and the concentrations are constant. And again, what's important to note here is there's a mixture of A, B, C, and D in that flask. Thanks for watching.